Welcome to Brain Vision.
Hello everyone, this is a solution to problem 38 of college physics. And the question is asking, why is it true that if you put a red filter in front of a light bulb and then you let the resultant light shine on a grating, that you see wide bands of red colors in the interference pattern on a screen? So basically what happens is that when you apply this red filter, it allows almost all of the wavelengths from the white light to go through that are in a given wide band of red light. So yeah, so what happens, you put this filter in and then all sorts of red, deep red, light red, they all go through this filter. And then once they've gone through that, they become incident on this grating here. And then from the grating, they get reflected and diffracted in all directions. And so if you had just, let's say, a single wavelength, then you would only see little spots over, let's say, over here, over here, over here, and over here. And then that's the image that a laser would produce, for example, because a laser allows only a short width of wavelengths to pass through, or it only creates a short width of wavelengths. But then white light, which is generated by a light bulb, creates all sorts of red light with all sorts of wavelengths that are allowed by the spectrum. And so these all differ differently. And so let's say that, one wavelength of red comes in here and it diffracts. And let's say that it goes on over here, for example, on the screen. So this is our screen here. And then another wavelength of red comes in. So let's say that this is wavelength 1, this is wavelength 2, and then wavelength 2 reflects over onto here. So you have that this is theta 1. So this is the angle, or this is the deflection angle of the first wavelength, and this is the deflection angle of the second wavelength. And then so on and so forth. You have more and more of these coming in. So you have all of these different wavelengths diffracting at different angles, which then produce these wide bands on the screen.